Alright, Minkowski's inequality, take two because I messed up the first time. So, let P be in one open interval from 1 to infinity, and let F and G be in LP of R. This is the space of continuous, or this is a space of functions which map from the domain in parentheses here, which is R, into R. We always assume that the codomain is R, and we also assume this is the space of functions whose p-norm is finite. So it says here in the problem that the p-norm of f and the p-norm of g are finite. That's equivalent to saying that f and g are in LP of R. So, by the way, so for this proof, we're essentially following the proof from Fallon Theorem 6.5. And we don't use this whole strange f plus g to the p is less than or equal to 2 to the p whatever. We don't need it. So we're just going to ignore it and continue. So letting q be the, what is it, the conjugate exponent or whatever to p, so it's p over p minus 1. What we need is we need p inverse plus q inverse to equal 1. And of course, with this choice of q, we know that this is going to give us this, and then this is just precisely p over p, which is 1, which is exactly what we need for Holder. And we also have this useful fact that if we take this p minus 1, multiply it, or move it to the other side, and take the q, move it to the other side, we have p minus 1 equals p over q. Then by Holder's inequality, we have the integral of f plus g to the p d mu. Well, what we can do is we can factor out one factor of f plus g to the p, because p is strictly greater than 1, so we can factor out one factor of it. So we'll have integral of f plus g times f plus g to the power of p minus 1 d mu. So the norm of f plus g is less than or equal to the norm of f plus the norm of g. So we can break this up, and then you can break it up into two integrals, and so we get the integral of f times f plus g to the p minus 1 d mu plus integral of g times norm of f plus g to the p minus 1 d mu. Okay, and now we apply Holder's inequality using using p and q here. So what we have is we have the one norm of the function f times norm of f plus g to the p minus 1. So we can take the p norm of one of these and the q norm of the other. And the way that we want to do this, which will make this work, is that we do the p norm of f and then the q norm of the absolute value of f plus g to the power of p minus 1. And this sort of just works out magically. Which is why it's really good that they gave us the hint here, because there's really, I don't think there's any good reason why you should think that this will work, but it just sort of magically works out. Okay, so we have this, and then we can factor out the norm of f plus the norm of g. So this is going to be equal, so we have p norm of f plus p norm of g times, and now we have this q norm of f plus g to the p minus 1. So how can we rewrite this? We can write this as the integral of f plus g to the power of p minus 1 over q times, and that whole integral to the power of 1 over q. But it's p minus 1 times q, then raise that entire integral to 1 over q. But remember, we have p minus 1 is equal to p over q. So this p minus 1, we replace that with p over q, and then when we do this integral formula, we have a q here, then we have d mu, and then we have 1 over q on the outside. And so the q's and the exponents here magically cancel out. And so what we end up with is this is fp plus gp times the integral of f plus g to the p d mu to the power of 1 over q. Okay, so we have that, and so we now are going to use this fact to write an inequality in terms of f plus g, p. So remember, this is the integral of f plus g to the power of p d mu to the power of 1 over p. But 1 over p, let's see here, if 1 over p plus 1 over q equals 1, then 1 over p is the same as 1 minus 1 over q. So this is precisely the integral. And by the way, I'm writing out more steps than Folland writes in his proof. So it's not really necessary to write out all of these steps, but I think it's nice. Okay, so now we have something raised to an exponent, but this exponent has an addition in it, and so we can break it up into two separate things. We have the integral of f plus g to the p d mu times the integral of f plus g to the p d mu to the power of minus 1 over q. Okay, but look, on this thing on the left, we have the integral of f plus g to the p d mu, and now we can apply the inequality from the previous equation, or we can apply the previous inequality. So this whole thing is less than or equal to f p plus gp times integral of f plus g to the p d mu to the power of 1 over q, and now we're multiplying by f plus g to the p d mu to the minus 1 over q. And these things like magically cancel out. So we just end up with, oh, that's a plus. Okay. fp plus gp. And this is exactly what we want, as desired. So that proves Minkowski's inequality for the case of p being strictly between 1 and infinity. So if p equals 1, the inequality is trivial. And why is it trivial? Because it ends up being the one norm of the norm. Basically, it just follows from the triangle inequality. We know that the norm of f plus g is less than or equal to the norm of f plus the norm of g. And so you just take integrals, and then that's Minkowski's inequality for p equals 1. Also, if you look at this, I don't think it's really necessary to say anything oh! Yeah. Wait. Yes. Okay, so why is it... Okay, wait. So that's interesting. I guess it is important to know that f plus g of the p is finite. Because otherwise you can't take the negative 1 over q root of it. Because then you're taking... like, you're dividing by infinity, which gives you 0, which is not okay. So, is that proven in Folland? It should be. And it should be a straightforward fact. Hold on. I didn't think about this. Okay, so the inequality, this inequality shows that f finite. So you do have to show that the p norm of f plus g is finite, because that allows you to... Because if the p norm of f plus g is finite, then that means the integral of the norm of f plus g to the p is also finite, because you're just taking the... you're taking a finite number and raising it to the power of p. And that's how you go from the p norm of f plus g to just the p norm of f plus g, but without that 1 over p exponent on the outside. And so, yeah, I didn't take the time to go through and prove the inequality that f plus g to the p is less than or equal to 2 to the p times the norm of f to the p plus the norm of g to the p. But it should be a straightforward fact. Let's see here. I'm trying to think if I can sort of do this on the fly, and I'm not really coming up with anything. So yeah, I don't want to like waste a bunch of time and get stuck trying to figure this out on the fly. But this inequality shouldn't be too difficult to figure out, and so once you have it, you know that the integral of f plus g to the p is going to be less than or equal to the, let's see here, the integral of 2 to the p times the norm of f to the p plus the norm of g to the p, and integrating 2 to the p is just going to give you something finite. Yeah, because that's just a constant, so you just pull the constant out. Then you're just left with the integral of f to the p plus the integral of g to the p, and those two are obviously finite because we're assuming that f and g are in LP. Okay, so I might come back at the end and prove the inequality that's stated here if I feel like it's slightly non-trivial, but if it ends up being trivial, I'll probably just skip over it. Okay, back to where we were in the proof. If p equals 1, the inequality is trivial. What about if p equals infinity? Taking the limit as p goes to infinity yields, by exercise 1.5.2, which basically says that the infinity norm is the limit of the p norms. So f plus g infinity is precisely the limit as p goes to infinity of, I should not break that up. F plus g infinity is just the limit as p goes to infinity, f plus g p, and every f plus g p is less than or equal to f p plus g p, and so you could just take the limit of this inequality and it will still hold, but then this limit is precisely f infinity plus g infinity, and so it holds as desired. And so we've done so we've proved this for p between 1 and infinity, and we've proven it for p equals 1, and we've proven it for p equals infinity, and that's all we needed to prove. And so we are now done with this exercise. And yeah, still recording in a hotel, so sorry about the planes, but that's just how it is. Alright, so I've decided that the proof that f plus g is in LP is very slightly non-trivial, so I'll go ahead and prove it. Basically what this is part of is proving that LP is a vector space, meaning that you can add things together and multiply by constants. It's obvious that you can multiply by constants because if you just take a finite integral and multiply by a constant, then you just end up multiplying by a finite number, and so it's finite. Well, I guess no. In the vector space definition, it's not just being finite. It's about you have to be able to pull the scalar out. So it's slightly more complicated. You could prove that LP is a vector space, but f plus g is in LP because you take f plus g to the p. So f plus g is certainly going to be less than or equal to 2 times the maximum of the norm of f plus the norm of g. So I guess the way that you can write this is f plus g in absolute value will be less than or equal to the norm of f plus the norm of g to the p. And so this is going to be, and by the way, this is for any x. So is that necessary? Let's include that. Why not? I have time. If you don't, you can just fast forward a little bit. So this to the p is less than or equal to, just by the triangle inequality, f of x plus g of x. This whole thing to the power of p. And so this is going to be less than or equal to 2 times. So one of these two things is going to be larger. And so we could just take 2 times the larger one. And that's only going to make this thing bigger. So maximum of f of x, here, I'll put this down here. It's less than or equal to the maximum of f of x and g of x. And we have to multiply this by 2. And then this entire thing is being raised to the power of p. And now we can take the 2 times 2 to the power of p outside, and then we're left with the maximum of f of x and g of x to the power of p. Now if we look at this, taking the largest one is certainly going to be less than or equal to taking both of them and adding them together, because these are just two positive numbers. So what we end up with is we can just write this as f of x plus g of x to the p. Wait a minute. Oh, right, because this is the max of f of x to the p plus the max of g of p. Okay, so if we factor this out, what this is going to be, the maximum of f of x, this thing to the power of p, and g of x to the power of p, because we're going to be taking the pth power at the end, and that's not going to affect which one is larger, so we can just bring the exponents inside. So if we have the maximum of these two things, then that's certainly going to be smaller than just taking both of them and adding them together, because we have two positive numbers. So for every x, f plus g to the p is going to be less than or equal to this thing. So if we take the integral, so let's see here, f plus g p norm is going to be integral f plus g to the p d mu 1 over p. It's going to be less than or equal to integral to the p, then we've got f to the p plus g to the p d mu to the 1 over p, which is less than or equal to to the p. Well, I guess we'll bring the 2 out front, so this is going to be 2, and then we're going to have integral of f to the p d mu plus integral g to the p d mu to the 1 over p. And then let's see here. Can we just like do this? It's going to be less than or equal to 2 times. Then we take 2 times the maximum of integral of f to the p d mu, integral of g to the p d mu, 1 over p. which is going to be precisely equal to 2 times 2 to the p times the maximum of p norm of f, p norm of g, which will be finite because p norm of f and p norm of g are both finite. This seems a little unnecessary. I feel like I'm doing the same thing twice here. It's a little strange. Let me just make sure. But yeah, I don't think I'm messing anything up here. It's possible that I'm including too many steps, but I don't think I'm making a mistake here. It does seem, because we're doing this thing like this, taking the maximum thing in order to get the inequality to work. I feel like we're doing it twice, and that shouldn't be necessary. But I don't know, maybe it is. Well, maybe we could start. Yeah, we might just be able to do it straight from the starting with the p norm of f plus g. But in any case, this is a proof of the fact that the p norm of f plus g is going to be finite so long as both the p norms of f and g are finite. And so that means that f plus g is an LP. And so when we go through the proof and we take the we take integral of f plus g to the p and we raise it to a negative power, that's well defined because we're taking a positive number to a negative power, which is completely fine. All right, and so having wrapped up that detail, we are now officially done with the exercise.